Recursion is a programming concept where a function calls itself to solve smaller instances of the same problem. Another definition. Recursion is a method of solving a problem where the solution depends on solutions to smaller instances of the same problem. Or, it is a situation where you do something and depending on the results, you might do it again. In programming, recursion occurs when the function calls itself. While mathematically elegant, recursion is notoriously difficult to grasp, because it requires thinking about problems in a fundamentally different way than interactive, iterative approaches. I would say it defies the natural linear flow of things. Unlike loops, where execution flows linearly, recursion builds up a hidden call stack of function invocations that must be mentally visualized. Recursion requires defining when the function should stop calling itself, the base case, without which infinite recursion occurs. Each recursive call creates its own execution context, with separate variables, making state tracking complex. This program demonstrates how recursion works by showing the call stack and execution flow of a recursive Fibonacci sequence calculation. And by the way, I assume you know what the Fibonacci sequence is and what a call stack is. The HTML document creates a dark-themed page with a gold text display area that will show the recursive Fibonacci calculation process. In short, HTML and CSS are basic, just to organize the display area for JavaScript. The JavaScript implements a recursive Fibonacci function with special visualization features. The function captures and passes the JavaScript call stack using new error.stack to determine the current recursion depth. This allows the program to visually indent each recursive call based on how deep it is in the call stack. For each function call, the program logs the function entry with proper indentation showing the call depth, the parameter value being processed, the return value when the function completes. When the Fibonacci function receives 0 or 1, the base cases, it immediately returns that value, which stops the recursion from going deeper at that branch. For values greater than 1, the function calls itself twice, once for n-2 and once for n-1. The results of these calls are summed to produce the Fibonacci number for the current n. While all recursive calls complete, the program displays the final Fibonacci number for the input value. The visualization shows how the recursion builds up a stack of calls, moving downward with increasing indentation, and then unwinds the stack, moving upward while returning values. Each recursive call waits for its child calls to complete before it can finish its computation and return, demonstrating the last in, first out, LIFO nature of the call stack. I hope it all will be helpful. Now I will scroll the file. That's all for now. Have a nice one.